You ever look at a bunch of numbers and just get the feeling that there's a secret story hiding inside them? Well, you're usually right. But to actually uncover those stories, to figure out what the data is trying to tell you, you need the right set of tools. So today, we're going to crack open the Data Detective's toolkit and see what's inside. Think about a question like this one. It feels like there should be an answer, right? But how would you actually go from just a hunch to real solid proof? This is exactly the kind of thinking we're going to use to crack our first case. So our first mission is all about finding these hidden connections. We want to know if two completely different things, like say a person's gender and their opinion on school uniforms, are secretly related, or if it's all just random coincidence. Okay, our first tool for the job is the contingency table. The best way to think about this is like our official case file. It just neatly organizes all the evidence for us. It shows us exactly how many people fall into each little box. How many males said yes to uniforms, how many females said no, and so on. It lays out all the facts of the case perfectly. Now, every good detective has to start somewhere. In the world of data, that starting point is called the Null Hypothesis. It's a really simple idea. We start by assuming there's no connection at all. We assume gender has absolutely nothing to do with uniform opinions, until the evidence is so strong it forces us to think otherwise. It's basically the innocent until proven guilty rule, but for data. So here's where the real investigation begins. We compare two things. On one side, we have our observed frequencies. That's the real evidence, the numbers we actually collected in our survey. And on the other side, we calculate the expected frequencies. This is what the number should look like if it was all just pure random chance. The whole case boils down to one question. How big is the difference between these two pictures? All right, so how do we actually measure that difference? For that, we need a special kind of tool. It's like pulling out a magnifying glass to get a closer look to see if the little details in our evidence are actually significant or if they're just, random noise. And that magnifying glass is the chi-square test. Its entire job, the only thing it does, is to calculate one single number that tells us just how big the gap is between what we actually saw and what we expected to see by chance. A really big gap suggests something real is going on. A small gap, well, it's probably nothing. But how do we know if the gap is big enough? Well, that's where we look at something called the p-value. Just think of it as a surprise-o-meter. It tells you the odds of seeing evidence this strong if our original innocent until proven guilty idea was true. So super low p-value means your results are incredibly surprising. So surprising, in fact, that we have to throw out our original assumption and declare that, yep, a connection most likely exists. Okay, let's switch gears and open up our second case file. This time, our mission isn't about finding a hidden connection, it's about grading a prediction. Imagine you've built a new spam filter, or maybe you're trying to figure out if a fortune teller is the real deal. How do you know if you can actually trust what they're telling you? I mean, on the surface, this sounds amazing, right? A 95% accuracy rate? But wait a minute, what if 99% of all your emails aren't spam anyway? A really lazy filter that just marks everything as not spam would be 99% accurate, but it would be completely useless. This just goes to show that we need a much better way to grade performance than just looking at accuracy. And that brings us to our second major tool, the confusion matrix. Now, don't let the name scare you. Its whole job is to bring clarity, not confusion. It's just a simple grid that lays out every single possible outcome. Did the filter say spam when it really was spam? Did it say spam when it wasn't? It tracks every single hit and every single miss. Let's break this down box by box. First up, the true positive. This is a home run for our filter. It correctly identified an email as spam. It called it, and it was right. That's a great catch. Now for a really bad error, the false positive. This is when the filter shouted, spam! But it was actually that important email you were waiting for. This is a false alarm, and it can be a huge, huge problem. That email might be lost forever. Next up is the true negative. This is our filter just doing its job perfectly and quietly in the background. An important email comes in, the filter correctly says, yep, this is fine, and lets it through to your inbox. Another correct call. And finally, we have the other kind of mistake, the false negative. This is when a real piece of spam just slips right past the filter because it was incorrectly labeled not spam. This is a mess, and it's the annoying reason you still get junk in your inbox. Okay, so now that we've sorted every single prediction into one of these 4 boxes, we can finally create a really detailed report card for our model. We're going to use the numbers from our confusion matrix to calculate its final grades. So first up is accuracy, the one we started with. And the formula is super simple. It's just the total number of correct calls, that's the true positives plus the true negatives, divided by the total number of predictions made. So accuracy just answers one simple question. Overall, how often was our model right? And like we said, it's a fine place to start, but it really doesn't tell us the whole story. Now for a much more specific grade, precision. This one only looks at the times the filter predicted an email was spam. The formula is the number of correct spam predictions divided by the total number of times it cried spam. So precision asks a really crucial question. Of all the times my filter shouted spam, how often was it actually right? If you have high precision, it means that when the filter flags something, you can be super confident that it's correct. You get very few false alarms. And our final metric is recall. Now this one looks at the problem from a completely different angle. It takes the number of correct spam predictions and divides it by the total number of emails that were actually spam to begin with. And this gets to the heart of what recall is all about. It answers the question, of all the spam that actually existed out there in the world, how many did our filter manage to successfully catch? High recall means your filter is an amazing hunter. It finds almost all the real spam. So, to wrap this all up, we've just added 2 incredibly powerful tools to our Data Detectives toolkit. First, we've got the chi-square test, which we use to investigate if 2 different categories are secretly connected. And second, we have the confusion matrix and its metrics, which give you a full, detailed report card to grade how well any prediction is performing. And look, this isn't just theory for a textbook. These exact tools are working behind the scenes all around us every single day. They help shape medical diagnoses, they help banks decide on loan approvals, and they're what powers your social media feed. So now that you know how they actually work, what are you going to see differently?